you, Kirsty. Hello, everybody. I want to start with an apology. I'm not 100% today. I've got some horrible lurgy, and yeah, if I go a little bit croaky, I have to mute myself for a coughing fit. I apologise for that. But Charlie's promised to do all of the intellectual heavy lifting if my brain's not quite at 100% today. So yeah, welcome. It's really lovely to see some familiar names, and it's also really lovely to see some unfamiliar names. So whether you've been to one of these before or this is your first time, you're very welcome. I'm Alison. I worked for the Enrich project in Cambridge from 2009 to the end of 2020 when I became a freelance maths consultant, and I do still work very closely with the Enrich team whenever I get a chance. And we've got Charlie with us as well, who is the Enrich secondary coordinator. So I don't know if you want to say a few words before we kick off, Charlie.
Just hello everyone.
So what we're looking at today then is we're going to be looking at coordinates and vectors. We're going to do a little bit of a deep dive into some of our favourite rich tasks, enriched tasks for teaching coordinates and vectors, and talk about why we think that these are important problems to be part of a student's mathematical journey, to talk about how this type of problem solving and working on rich tasks can really help students to build up their mental models for thinking about coordinates, and particularly with respect to vectors, how this is one of the topics that whenever I'm working with GCSE age students, they always do this big groan and they go, oh no, not vectors, which is a real shame because for me, vectors are such and such a powerful tool. They allow me to solve different types of problems. And I honestly think part of the problem is that they have this air of mystery around them. They're called vectors, which is a slightly scary sounding name. And students don't necessarily have lots and lots of experience of working with vectors. So we're going to talk a little bit about some of the things that you can do to develop fluency at working with vectors, but also to unlock some of that problem solving potential. But I think let's get started on a problem straight away. And I'm going to share my screen to start us off with this, I think. So hopefully if I do this, everybody can see a page from the software GeoGebra. Now, some of the problems we show you on the Enrich site today have GeoGebra embedded within the problem. But most of the time when I'm working with coordinates and vectors, even if there's already a pre-made app or applet, I often use GeoGebra to build my own things in front of the students as they are watching, because it's a really powerful tool to introduce them to and for them to see what's going on. So all I have marked on this grid at the moment is the point 2020. And I'm going to put some other points on. I'm going to hide the algebra view because I don't want you to be able to see that just yet. But I'm going to put a couple more points on the grid, and they're going to be called, oh, it's not labeled them. So let's give them a label. That's going to be called point A, and that one is called point C. I don't know why it's decided to call them A and C, but let's just go with it. And as I move these points around, let's put one there and one there. And I'd like you to imagine how your students would approach this task as well. Have a look at those points, and can you work out the coordinates of point A and point C? I might just, can everybody see the grid okay, or do I need to make the grid slightly darker? Also, my chat's disappeared. Where's my chat gone? There's my chat. Excellent.
I can see very clearly, Alison.
Okay, I will trust that if Charlie can see it, then younger eyes can see it too. Brilliant. Okay, so Leonie's gone straight in there with an excellent point. It entirely depends on the scale of the grid that I've used. So whenever I'm working with coordinates, I need to be able to see the axes to be sure of the scale. So if I tell you that it is 1 square per unit, so when I move 1 square across in the x direction, my x coordinate will increase by 1. When I move 1 square up, my y coordinate will be 1. So hopefully that gives you enough information to work out the coordinates of A and C. Out the coordinates, Alida has suggested 1922 for A and 2320 for C. Stanley said the same. So what do you think might go through a student's head if we pose this question in the classroom?
Okay, so I might be tempted to do C first because I think I'd find it easier. And all I need to do to get from your original point to C is to move 3 units across, and I'm going to stay at the same level. So the y coordinate's not going to change. So I'm going to get to 2320, just like the 2 solutions that have been posted in the chat. A is marginally more difficult, but not very difficult. And I'm thinking I've got to go across before I go up. I tend to remember that by thinking about going along the corridor and then up the stairs.
We might have to talk about that.
Okay. And I'm having to go left. So I'm going sort of in the negative direction, or I'm going closer to the origin. So the x coordinate is going to be 1 unit less than 20. But I'm going two floors up, so to speak. So the first coordinate is going to go down to 19, and the second coordinate is going to go up to 22, which again is what's been posted.
Lovely. I really enjoyed your storytelling there, with the exception of the mnemonic, because famously mnemonics never work for me. So whenever someone teaches me a mnemonic, it's like, great, now I've got 2 things to remember, because I've got to remember the thing and then also this extra story you've given to help me remember the thing. Also, the house that I grew up in, we had a corridor, but it was upstairs. And so in my house, you literally went upstairs and then along the corridor. So we do need to be a little bit careful, but helping students to remember whatever way works for them that they're doing. The horizontal axis is the x-axis. Now, I do have a mnemonic that I liked for that, because when I was in year 8, Mrs. Hardy used to say to me that the horizontal axis was the x-axis because x is across. Yeah. So yes, thank you, Mrs. Hardy, for that. The only mnemonic that's ever worked for me. But yeah, so starting with these, I mean, we can. The nice thing in GeoGebra is, of course, we can go into the settings and say, show me the value of these points. And then it will show you, and you can see, yes, we are absolutely right with that. And so we can have some points on screen. And if I want to include the axis on the screen, I can do, but sometimes it's nice to be working without axes. And so this is why for this problem, we're using the point 2020 as our origin instead of 0, 0, because we want to get used to students thinking about the relative position of things on the grid. Okay, next challenge then, and this one might take people a little bit longer, so I'm going to give you a little bit longer to work on it, but as soon as you have an answer for me, you can drop it in the chat. So my question to you is, if I were to move these points around, I'm going to fix the first point 2020. So I'm just going to go in here and say fix that object. So I can move this point, I can move this point, but I can't move that one. And so if I leave these on fairly random numbers, then hopefully that will help you remember which of the 2 that I'm moving. So if one of my coordinates is 2020, can you find places to put the other 2 coordinates so that if I joined them together, I would have an isosceles triangle? So if I draw the triangle formed by these 3 points, this is clearly not isosceles, because if I were to show the length of this here, this is 5, this is 12, and this is 15. So I don't have 2 sides the same, so it's definitely not isosceles. So can you find positions for my points A and C so that I get an isosceles triangle. And if you have found one set of points, I would like you to see if you can find any families of sets of points that give you isosceles triangle. So I'm going to give you a little bit of time to think about this. If you don't want any spoilers, don't look at the chat because spoilers are starting to come in, which is brilliant. But we'll just sit back and have a couple of minutes of thinking time, and then we'll talk about our answers to this problem. The chat, if I was using this activity in the classroom, I might start in a similar way, getting students to suggest points that could be isosceles triangles. I'd want them to have some thinking time on their own and then some pair work justifying to a partner that what they'd come up with was isosceles. In a moment, we can switch over to Charlie has a visualizer so he can show us some of the paper and pencil work or whiteboard work that you might do. I'm going to sneeze, sorry. Sorry, I thought I'd done all the sneezing while I was muted. Do it some of the whiteboard work or plain paper work that you could do to be talking about this without having to have the scaffolding of a square grid like GeoGebra or squared paper or dotty paper. But let's have a look at some of your suggestions using GeoGebra to check for isoscelesness, which is totally a word. And of course, you've done the wonderful thing that maths teachers do of instead of giving the actual coordinates, you've gone straight for the algebra and given me the families of coordinates. So I'm going to have to do a little bit of deciphering. Charlie, I might make you do some of the deciphering. Can you choose one of the comments from the chat and tell me about the families that they've come up with some actual numbers that I can move it to and put in?
Okay. Well, before I do that, what I find really interesting is, if I'm correct, all the examples that have been posted have 2020 as the vertex which has the angle that has not got a partner that is identical. So if you think of, maybe a typical isosceles triangle where the two angles at the bottom are equal and the third one is different. I think all the examples that have been posted have got the angle at 2020 being the odd one out.
Okay, that was a thing that I was interested in seeing, but because of the way my brain works and at the moment doesn't work, I sort of wanted to plot some of them first. Okay. To see that. So let's have a look to see what it is that you mean. Okay,
so tell me again what it is you'd like me to...
Okay, so I can see Joe's done a lovely comment that says 20 minus a y and 20 plus a y. So I need to choose a value of a and a value of y to be able to draw that. So if a was 1, then it would be 19 and 21. And then I think my y value can be anything. So it's making a family by walking these up like this. So I think that's what Joe means by that family.
Would you mind removing the length of the sides because it's getting a little bit cluttered?
Consider it done. You also want the length of the coordinates still though, don't you?
Yes, please.
I mean, if I'm honest, part of this is me showing off how easy it is to do GeoGebra on the fly in front of a class once you know a few tips and tricks, because I want to encourage more teachers to use it in their teaching. I might be doing some training at some point on GeoGebra. It's not set in stone yet, but people who follow me in all the usual places, if you would like GeoGebra training so you too can be a power user, then pester me on social media and we'll make that happen. So yeah, this
and Alison, yes? You've chosen your y to be greater than 20.
But I could easily well go down here, couldn't I?
Yeah.
So this would also satisfy Joe's family. Um,
It,
and
you have all the family, yeah, you've got all the isosceles triangles. Uh, this is a conjecture where one of the sides is horizontal
mhm,
and the vertex at 2020 has the angle which is the odd one out.
yeah. And then I think this other one that Joe suggested, which was x 20 plus a and x 20 minus a, I can pick an x value, let's pick 18, and then I can have the same below as above. So I could have this one, or this one, or this one. And that's not quite right, is it? That's better. No. Okay, there we are.
Can you just clarify? Is that the one x 20 plus a and x 20 minus a?
Yeah, so the x coordinate is staying the same at 17, and then I've just got the same amount above and below 20,
So that's
like
got
that.
that'll be all the families of isosceles triangles where one side is vertical and 2020 is still the odd one out.
Hmm.
But there are others, aren't there? I'm just thinking there must be some isosceles triangles where none of the sides are either horizontal or vertical.
So I could have something. So to make this triangle,
I wondered whether to leave the challenge for the participants.
all right, I'll put that triangle up then, because there I've got a horizontal and a vertical side.
Brilliant, brilliant.
Okay.
Okay.
So
So
shall we leave people for a moment to see if they can find one like the one I was trying to make? I was just trying to see if I'd understood your question correctly, really.
okay, so far we've seen all the triangles have either had a horizontal or a vertical side, and my challenge now is can people post suggestions for triangles where none of the sides are either horizontal or vertical?
And can I add an extra thing that it would be really lovely if people can post things without the algebra in, so some whole number examples first, just so that my poor cold-ridden brain doesn't have to work quite so hard.
That's very nice that you've just drawn, but I think it still has one vertical side. But it is not part of the families that we'd been looking at. So
It does. I drew it because it was like, this doesn't look like it's going to be isosceles. Oh, it is, but for a really interesting reason.
it would be quite nice to have an example where 2020, the angle at 2020 has got another partner. Ah, no, okay. Cool. Yeah, so far 2020 has always been the odd one out.
That looks isosceles.
Yes,
So that was a leader's example.
but 2020 is still the angle that
Yeah.
hasn't got a partner. 2020 is feeling a bit lonely, I think.
2020 is fine. She lies on the line y equals x. She's doing fine in her life.
And on the line x plus y equals 40.
Oh, oh, that was Tina's example.
So now 2020 does have a partner.
Yeah.
Okay, so how about one like that, but where there is no horizontal or vertical line? Ooh. What I like about what's happening, Alison, is that I could be working on my triangles, but I could also every now and again be looking at the screen and trying to figure out. You're posting without saying anything, so I've got a choice of whether to look at what's happening on the screen and give me some ideas and think, oh, yes, I can adapt what I can see on the screen, or I'm not looking at the screen and I'm doing my own thing and posting that, and you are you're showing us without, and I'm often thinking, oh, is that isosceles or not? And
Yeah. So I mean, it might be nice if we switch to the visualizer just for a moment, because another strategy that I might do for this in the classroom, if I just stop my share, I might want to collect students' work on the whiteboard and collect their examples and non-examples, but I don't want to have to draw out a whole coordinate grid. So I can use a piece of plain paper and just do sketches and let my sketches capture the important information of it. So why don't we draw a couple of these examples on plain paper and talk about how we might show whether they're isosceles or not, just from that. And oh, I can see that you have been busy doodling while we've been talking.
this is me doodling. I'm going to get a new sheet so that you can see it, but I've just been doodling for myself with paper and pencil. Okay, so give me something you'd like me to draw.
Okay, so there's one that Leonie's put in the chat, which is 2020, 1525, and 1823. So 1525, I know that I'm going to have gone back by 5 and up by 5.
Okay, so 1525.
Yeah.
I'm writing this. Let me start again. I'm not sure I've written large enough.
I could read it, but
so 20.
So there's our 2020. So 1525, I know I need to go back 5 and up 5 for that. So it doesn't matter if these aren't exactly. This is about helping students to be able to sketch things. And then I've got the point 18, 23. So I've gone back by 2 and then up by 3. So from 2020
to 18, and then
yeah,
up
and
3.
then up 3. Oh, we've had a correction. 17.5 and 22.5 instead of 18 and 23, presumably.
Okay, so 17.5 is exactly in the middle
Yeah.
of this line of this, because that was
So
5.
I think this is going to be an isosceles triangle where it has an angle of 180 and 2 angles of 0.
That is what I'm worried about, because
No, I'm not worried about it, because if this happened in my classroom, it would be a wonderful opportunity to talk about limits and about how, if I describe a family, because I'm now imagining the line joining 2020 and the line joining 1525 and drawing that perpendicular bisector of that line, which would pass through the point 17.5, 22.5, but going in the perpendicular direction.
you want a line through
Yeah,
there.
yeah. And if I wanted to describe the whole family of isosceles triangles, I could say I can put my point anywhere on that line, and because it is the perpendicular bisector, I know, not using coordinate geometry, but using just, constructions, straight edge and compass constructions, this is going to give me a whole family of isosceles triangles. But then the one example in the middle is a non-example, because it would be the isosceles triangle where its angle was 180 degrees. So that would be a really lovely talking point and teaching point about how something is continuously varying, and then eventually it gets to the point where it's not an isosceles triangle anymore, because it is just this straight line instead.
So what's really nice about these triangles, Alison, is that 2020 has got a partner, which is what I was asking for, and none of the sides are either horizontal or vertical. So this, and it's quite nice that we can describe the points along this line as points where the y coordinate is 5 more than the x coordinate. So we'll be able to find lots of points along this line, which can partner these two coordinates. So Andrew suggested 1823 works. Yes, y being 5 more than the x coordinate.
Yeah. And so this is also a really nice opportunity to show that we might want to use this problem to get students in their early discovery of working with coordinates, getting them becoming more fluent about doing these sorts of things, about saying, if I go back 2 and up 2, where will I be? If I go down 2 and right 2, where will I be? And moving around the coordinate grid. But because you are familiar with equations of straight lines, you've chosen to go into that representation for it. Now, you probably wouldn't make that pedagogical choice if you were teaching students who had not yet met straight line graphs. But if you are doing this problem as part of some revision for year 10s or year 11s who have already met straight line graphs, then looking at how isosceles triangles connect with straight line graphs and looking at how perpendicular bisectors relate to what's going on the coordinate grid would be a really nice direction for this to take. And I know one thing that lots of teachers value about using rich tasks in the classroom is that you can be using the same task in different ways with different groups of students. So it feels as if on this piece of paper, we've taken a step upwards and gone to a different level of thinking about coordinates, because we're now thinking about the relationship between the X and Y coordinate and what that does for straight line graphs. Now, this is only the introductory problem. This isn't even the problem that I wanted to share as it appears on NRICH. Have we got time to look at the version with the area constraint? I hope we have.
Yes, I'm sure we do. Before we do that, Alison, you were initially, when we were trying to picture where 1525 went, I think you talked about going across 5 to the left and then 5 up. And so we sort of knew the coordinates of this point over here. And it's quite nice imagining or getting, because you talked about students working on mental models, and anybody who joined us for a previous webinar, we did a problem, or you might remember what it's called, Alison. All of a sudden, my mind's gone blank. About route to infinity. And this idea that, well, if I'm going to go from 1520 along this pink line, I can go one across and one up. And so I would get to 1621 and another one across and another up, and I'd get to 1722. And I'm increasing my X coordinate by 1 and my Y coordinate by 1. And a bit like siblings whose age is 5 apart, a year later, they're both 1 year older, but their ages are still 1 apart. And another year later. And 10 years later, they'll be 25 and 30. So they'll be 10 years older, but their ages will still. So this number will always be 5 more than the other. So even if they might not be able to talk about y equals x plus 5, they might be able to find the coordinates along this line where the y coordinate is 5 more than the x coordinate.
Yeah, if I can steal the screen share from you, I will just show route to infinity that you were talking about, because for people who haven't seen it, it's a really nice hopefully you can see this now. It's a really nice activity. You can do it at a very superficial level and just use it at the start of a lesson to say, where will the pattern go next? If I could pause it at any point, how do you know where it'll go next? Will it continue forever? There are lots and lots of suggested questions, and if you look at the top of the problem, there's the tab for the teacher's resources at the end, and that suggests in here the sort of questions that you could be asking in the classroom while working on it. I'm going to show you then what the actual problem about isosceles triangles looks like on NRICH, because we've just used the idea, I have a vertex at 2020 and I'm drawing an isosceles triangle. The problem as it appears on NRICH puts in an extra constraint and says, can you also find ones where the area is 9 square centimeters? And in some ways, this is making our problem easier because we have an extra constraint. So rather than there being infinitely many answers, there are now only going to be finitely many answers. But of course, the idea behind it is, can you find them all, and how do you know how you found them all? And so it would be nice to give people a little bit of time to think about this, and hopefully, having looked at some of the possible families of isosceles triangles, you can now start to think about whether any of the triangles within that family have this property that the area is 9. Now, what you get in the NRICH problem for this is an embedded GeoGebra applet. So rather than having to make your own, you've got one here, and as you move it around, it is telling you that for each of these, it tells you what the area is and whether it is isosceles or not. I might not give this to students to play around with for themselves because there is a tendency to start doing it by pattern spotting and saying, okay, well, I can move these like this and the area is going up. So maybe if I move them back this way, I'll be able to get an area of 9. And so maybe I would have them working on pencil and paper first, but then this is really great to be a quick way to check it. So let's give everybody a couple of minutes to see if you can find one example of an isosceles triangle who has a coordinate at 2020 and an area of 9. Have I said all of that right? I think I have. Now, unfortunately, I did forget to say that we wanted to stick to whole number coordinates. So thank you to people who have found ones that have 0.5s in them. Unfortunately, the GeoGebra that I've made here in the problem only allows you to draw them on the grid points. And so I can't draw any of yours to check. But then, of course, this is a lovely opportunity to say, well, let's stick with the whole number coordinates first, and then we can use looking at how to check ones that don't have whole number coordinates as a sort of add-on. Okay, I've been putting in some of the triangles that you found as you've been finding them. And one thing I've noticed is that we've had quite a lot of triangles that are this sort of long, thin shape. They've got a base of 2 and a height of 9. So I know they'll have an area of 9 because base times height over 2 is going to give me 18 over 2, which is 9. But the nice thing is that I can have it down here like Lorna suggested. I can have up here like this, which is what Natalie has just suggested. I think somebody before had it something like that. And so there's lots of different places that we can orient this triangle. And so we found one that has an area of 9 and is isosceles. And then we can use our symmetry as we're rotating around the grid to find other examples. Has anyone found some examples that are a different shape than this? I think we had one further up, and I think Joe has just suggested one. So I can have 26, 20, and come on, there we are, and 23, 23. So this one's going to work because it's got a base of 6 and a height of 3. So 6 times 3 is 18. 18 over 2 is 9. And again, I'm going to be able to do the same sort of thing, aren't I? I'm going to be able to swing this point down here and this one down here and get another one. Or I could have this here and this here and get another one. So I can be sort of rotating this round. I can be reflecting it. I could have something like this, couldn't I? There we are. So it's sort of sitting on its point. So this is how we're going to start to get into the conversation. How do you know that we've found them all? Because if I'm making an area of 9, I need to have 2 numbers that multiply together to give 18. And so there aren't too many of those. So there's not going to be too many possibilities. Any thoughts, Charlie?
Are you asking any thoughts about how I'm going to convince myself I've got all the solutions?
Yeah, I actually just needed to mute myself for a second so I could blow my nose, which is approximately the color of Rudolph the red-nosed reindeer now. So, but yes, if we're restricting it to just integer points on the grid, how will I know that I found them all?
Okay, maybe I should scribble a bit. Let me share
Yeah,
my screen.
I'll stop sharing.
So I'm thinking, if this is 2020, then I can have isosceles triangles with a horizontal side going from in either direction from 2020, but I can also have them coming down. But I could also have, if that's 2020, I could have 4 in this direction. And there's my 2020. But I could also have sort of the pointy bit. So, sorry, that's very, okay. So once I've got one triangle, for example, let's imagine that this has got, I don't know, a base of 2 and a height of 9. I can replicate it 12 times because they're all, I'm just assuming they're all identical to each other. So this would be 2 here, and that distance would be 9. So once I've got one triangle that works, I can have it in 12 different positions. And I think there are only 3 triangles that work. Because of your constraint that I can only have whole numbers, I'm thinking I can have a base of 2 and a height of 9, because I need the base times the height to multiply to give me 18, because the area of a triangle is base times height divided by 2. Now 3 times 6 is 18, but I can't have a base of 3 because the midpoint would have a half coordinate. But I can have a base of 6 and a height of 3. Because 6 times 3 is 18. And the final triangle that I can have has got a base of 18 and a height of 1. So these are the only 3 triangles I can have because they all need to have an even number base. So I can't have bases of 1, 3, or 9. 1 times 18, 2 times 9, 3 times 6 are the factors of 18. So I've considered all the pairs. And each of these can be put in 12 different positions or 3 different families. So I think there are 36 altogether.
So I'm just thinking how lovely it would be in the classroom to have students coming up with those explanations, and they might not all get all of it. You might have different students contributing different parts. So one person might talk through why there are 4 ways of arranging the triangle so that it's got a horizontal base. Some might do the 4 ways where it's got a vertical base. Someone might do the 4 where it's the 20/20 that is the odd one out vertex. And then you might have different students identifying that the base has to be even, because otherwise you'll be on one of the halfway points between two coordinates. And then all together we're putting all of that information together to come up with a proof. And we know that proof is one of the things that students really struggle to do when they come to do their GCSEs, coming up with what counts as a good reasoned mathematical argument. The more opportunities we can give them to do that when they're younger, the more fluent that they're going to be in that skill by the time they meet it in GCSE maths. I think we should probably move on to another problem, shouldn't we?
Can I just add one thing? The very first time I saw this problem, I didn't solve it as quickly as I solved it this afternoon. The only reason I was able to talk through the 36 possibilities is because I've seen the problem before. Then Alison and I wrote the problem. We played around with it, and we thought about ways of convincing ourselves. So the last thing we want to do is give you the impression that we want, or that Alison's giving the impression that she's expecting students to come up with this very, very quickly. And I think it's really important to emphasize that mathematicians initially go through a stage of very messy work, which is really valuable and important. I've got my bit of paper here. And initially I thought there were 24 solutions until I remembered that solution. So initially I didn't get 36. I got 4 and 4 times 3. So 8 times 3, I got 24 solutions. But I sort of thought that it was, so I just checked, and then I remembered that one. So like Alison says, I like the idea that different people in the class are contributing, and eventually we form a picture. And then maybe after all that messy work, how can we convince ourselves that we've got all the possibilities? So this that I've offered is very sort of refined and so on, and there are lots of messy stages in between.
Yeah, it's one of the slight sadnesses of these sessions is that we would love to be able to give people a lot more time to explore the problems, but then at the same time, we kind of want to tell you the story of the problems so that you can, go away and uh, use them in class and not have to go through it all. But of course, we do hope that some people want to go through and explore some of these things a little bit further and look at how to use it um in a using it with different groups, using some of the ideas that we talked about with coordinate geometry and so on. Should we have a look at opposite vertices? Okay, so I guess maybe it would be good to use the Zoom whiteboard for this. So what I'm going to do is I'm just going to pop open a whiteboard and I'm going to screen grab the image from the problem for everyone to see. So the story here is that we've got some lines on a dotty grid and they are the sides of a square. And so the question is, can you figure out each of them is the side of a square. Can you figure out where the other three sides of the square I'm so sorry. Where the other three sides of the square will go. Now, I don't know if participants can draw on the whiteboard. If you can, and if anybody would like to, then if anyone wants to jump in and show where the other sides of the square would be. Oh, this is just beautiful. And what's lovely about getting this in a shared thing with everybody diving in like that is we've straight away got to something that might take students a little bit longer, which is that this doesn't uniquely define the square, because one side of the square I can sort of be doing like going above the line or going below the line for it. And so there are two different options for each line. There is a bigger question to ask here, which is, was there anything special about those three lines that I chose, or could we do this with any line on the grid? So if I drew any line on a dotty grid, can you always turn it into a square from there? And if so, how do you know? Because these three you all did seemingly with no effort at all. It just magically happened before my eyes, which I'm still delighted by. So Jo, when you've said any, is that to say any line will do? You can always make a square from any line? Yes. Okay. So count the squares across and up, and then repeat. Okay. So I think I know what you mean by this. Please do interrupt me if I say the wrong thing here. But I think what you're saying is that let's take the third one of these lines that I've gone back to and then up three to get the first line. And so then if I go up two and along three, then that's given me another line that is the same length. I know it's the same length because these two triangles are the same as each other. And I also know it's a right angle. And the question of how I know it's a right angle, I can do a little bit of angle chasing for this. This is a right angle triangle because it's on the grid. So I know that these two angles add up to 90 degrees. But then that angle is the same if I call that alpha and that beta. So alpha plus beta is 90. So this angle here must be 90. And a lot of you will recognize this sort of an image of a square with triangles wrapped around it from one of the nice visual proofs of Pythagoras that you can do. So I would spend a lot longer than this in class on this problem. I'm just trying to remember how to delete other people's annotations on the Zoom whiteboard. I know there's a way to do it. I could just add a new page, couldn't I? There we are. I could close it and reopen it. Is it going to give me a new? Yes, it's going to give me a new whiteboard. Because the question I actually wanted to ask was this, and you might want to spend a little bit longer thinking about it. So don't jump in and spoil this if you already know the answer. But these lines, instead of being the sides of a square, they are one of the diagonals of a square. So in the same way that you could take a side and turn it into a square, if instead I give you the diagonal, is there a method to figure out where it is? So if you've got some paper and pencil with you, you might want to have a little go at doing this. Don't draw on the shared whiteboard just yet, because that might give spoilers to people who are still thinking about it. But I'm going to give you just a couple of minutes to start thinking about how you might approach this problem, and possibly more importantly, what your students might do to approach this problem. Now, what I really love about the comments that are starting to come in the chat is that Natalie has used the problem that we already worked on to give some insight into this, because what we're looking for is two identical isosceles triangles using that line with 90-degree angles, so that the diagonal is splitting the square into two isosceles right-angled triangles. And so if we've got the perpendicular bisector, then we need to find the point on that that's going to give us the right angle. And that's very similar to what Alida has said, which is that the diagonals of a square are perpendicular and the same length. And so we know that if we can draw the other diagonal in, then, and this is what Leonie has suggested, do the perpendicular bisector and then look for where there are right angles. And so, yeah, we know that the diagonals of a square bisect at right angles. So if we're drawing the perpendicular bisector, then that's going to give us what we need. Now, students might not come up with this as quickly as maths teachers would do. So one thing that we might invite students to do is to think about this problem as a working backwards problem. So if I draw some squares and then draw some diagonals, what do I notice about the diagonals in relation to the squares? And then once you know that I can just do the perpendicular bisector, and effectively I'm just rotating the diagonal through 90 degrees. So I'm going to find that midpoint there, and then where's it going to need to go? This is so hard when you're poorly. Have I done that right, Charlie? Up to there and down to there?
Yes.
Thank you. And then up to there and down to there. And Joe has suggested thinking about vectors. So Joe gets my gold star because this problem appears on Enrich in two different forms. So the form that I've shared with you here is a problem called opposite vertices. And it is exactly the same underlying maths as a second problem called vector journeys. And so I'm just going to take a quick screen grab to show you what the same mathematics looks like in the problem vector journeys. So this is Alison's walk across a square park using the blue vector 2, 4, and then the black and the 3 red vectors are the vectors being the boundary of the park. And so this is a way to get students using the language of vectors to describe what they're doing for this problem. Because what I've got here is I've got the vector, the black vector is the vector 3, 1, and the next red vector is the vector -1, 3. And we can see that those two vectors together give us the vector 2, 4. So it's a really low stakes, non-threatening way into starting to do some vector addition. But then we can start to do some noticing and wondering, because I've got the vector 3, 1 and the vector -1, 3, and these are perpendicular. And the question that I want to shout out is, why does 3, 1 and -1, 3, why does that give me perpendicular vectors? And so this is starting to get us into some of the questions about lines on coordinate grids, because we're sort of implicitly thinking about gradient at this point. Because if I think about the gradient of that line, it would be 1/3. And then if I think about the gradient of this red line here, that's 1 and that's 3. So it is, it's effectively minus 3, isn't it? And so why are these two gradients perpendicular to each other? Charlie, do you want to jump in with anything? Because I feel as if I've said a lot.
Well, also that another vector that is perpendicular to 3, 1 is the vector 1, -3. Now, of course, those two vectors wouldn't align with the blue vector, which is the diagonal of the square you were looking for. Mm-hmm. But again, 1, -3 would also have a gradient of -3, So you've got a gradient of a third, you've got a gradient of -3, and the product is going to be -1.
Yeah, and this is starting to get us into some of the conversations. One of the big sticking points in vectors is that we often use position vectors and direction vectors almost interchangeably and don't always make it clear that that's what we're doing. Well, I mean, I shouldn't speak for everybody. There are good teachers who make it clear the distinction between position vectors and direction vectors. It is very easy to fall into the trap when you're familiar with vectors of becoming a little bit lazy with the notation, and that can lead to a couple of misconceptions with students. And so this problem, where we're talking about starting from a point and then doing some addition of vectors that gets you back to zero, it's then nice to be able to start talking about some of these properties of vectors.
Can you say a little bit more about the two distinct ways of thinking about vectors, Alison?
So effectively, when I'm talking about, hang on, I'm just going to try and make a little bit of room here. There we are, that's better. When I'm talking about a vector, I might be thinking about, here are my coordinate axes. I can have a point 3, 2 on my coordinate axes, and then I can have a vector 3, 2, and that is the vector that takes me from the origin to the point 3, 2. But of course, it's also the vector that takes me from this point to this point. And so this is when I'm using it as a direction vector. And so if I get into the habit of writing a coordinate as a vector instead, and sort of muddy over the fact that what I actually mean is the vector that is going from 0, 0 to 3, 2 is the vector 3, 2. Then if I'm implicitly using a coordinate grid, it can get very, very confusing for students, because I tell them that two vectors are equal, and then they say, well, they're not equal because they're in different places. And if you're very used to thinking in the mindset of coordinates and line segments, the fact that I'm telling you that these three things are all the same, they're all the vector 3, 2, there's a real instinct to say they're not the same, they're in different places. And so it's really important to be clear of what we're using the vectors for, and that vectors are tools that we can use to make our maths more easy. And then they're not, we don't have to feel intimidated by them. And so what I like about vector journeys is because it's a more intuitive way of working with vectors. It's only using fairly simple small vectors to do things, but some of the important properties of vectors are starting to come out of this, because once I draw a vector journey, so for example, if I started with the vector that goes across 4 and up 2, and I had that as the diagonal of the square, I can then start doing some of my midpoint analysis like I did when I was using coordinates, and say, well, the midpoint of that vector is going to be the vector 2, 1. And this is really common when you start doing vector algebra questions, being able to think about the vector A and the vector half A and what their relationship is, and that it's half the I component and half the J component. And so I found the midpoint, and then I can start thinking, well, where is the perpendicular line going to go for this? Well, if I've gone across 2 and up 1, and I want to be perpendicular, I have to go up 2 and then left 1. And so from the midpoint, I know where I'm going. And so then that's telling me where I'm going from the original because I've gone across 2 and up 1 and then up 2 and back 1. And so I can do the vector addition of 2, 1 plus, what is it? -1, 2 is equal to 1, 3. And so if I do the vector 1, 3, that's going to give me the next vertex. And then I can flip that round and say that if I do the vector 3, -1, which is going to be down there somewhere, it's going to give me the other vertex. And so, I mean, I'm doing this just very, very quickly because I'm very, very familiar with vectors. But over the course of a whole lesson, drawing lots of examples out, drawing them on dotty paper to see what's happening, then it's giving students lots of opportunities to practice vector addition and vector manipulation, but through a purposeful context, because they're trying to solve the problem of how to find these vector journeys from the diagonals. And the rather lovely thing, which I think I'm not going to spoil, I'm going to leave it for people to go away and explore if they've never explored this problem before. When we looked at the diagonal, when we looked at the sides of a square, Joe told us that any side of the square that is on coordinate grid points, I can draw 2 different squares from it, one going up and one going down. But if instead of the side I have the diagonal, I can't just draw any diagonal. There are only some diagonals. So here, where I chose 4, 2 as the diagonal, I chose that very carefully. And so one thing that you might want to go away and explore or look at the problem vector journeys on Enrich is, when is it possible to get a square and when is there not going to be a square on grid points? Obviously, if I'm allowed to go anywhere on the grid and I'm not going on integer coordinate points, then it's fine. But if I'm restricting things to coordinate grid points, what has to be true about the diagonals?
And a slightly different way of expressing the same problem, same question, is if I give you the coordinates of 2 points, can you look at those coordinates and tell me whether they can be the opposite vertices of a square? So you're given the coordinates of 2 points. Without doing any drawing, can you tell me whether they could be the ends of the diagonal?
And I think that's how it's expressed in the problem. Well, it's actually slightly different in the problem square coordinates, which was the other one that we wanted to share today. So I know we're coming up sort of 10 minutes from the end. I know that you've got a little bit of telling them how to find these problems on the site that you wanted to do. And so I don't want to eat into the admin time. But let's just share the problem square coordinates, which is very strongly related to what we've just done. And so this starts off, play with this interactivity until you can draw tilted squares confidently. I feel really confident about this because everything that I've just done in opposite vertices means that I know that if I choose any line for my first line, I'm not going to do something quite so big because then I'll have to count. So I can go 1, 2, 3, 4, 5, 6 across and 2 up. So now if I go back by 2 and up by 6, then I'm going to be able to draw a square with it. So this is more for people who've never done any work in this ballpark to start off with. But then the question that this is asking us to do underneath, it gives us a set of points and says, which of these will form a square? And so we've gone back from the abstract world of just working on a dotty grid to specifically working in the coordinates world. And this challenge of can you do these without plotting the points on the grid? The first time Charlie showed me this problem, I said, no, there's absolutely no way I can do this without that. That's literally impossible for my brain to do. And I suspect that people who can do this, that what they're doing is they are secretly plotting the coordinates in their heads because they have these magic whiteboards in their heads that they can draw things on. And I don't have that. I have aphantasia. So I don't see pictures in my head, which means that how am I supposed to know whether this is going to make a square or not? But I can do it by starting to look at the numbers. And I can start to do it by saying, well, as I'm going around from 8-3 to 7-8 to 2-7 to 3-2, how many am I going across and up or across and down to get to each of these things? And is that going to give me what I would need for a square? And so I'm thinking really clearly about the properties of squares. I know the four sides need to be the same length, and I know that the four angles have to be 90 degrees. So this problem is forcing me to think about two things. It's forcing me to think about the lengths of the sides, the distance between two coordinates, and the angles between two lines. And those are two of the topics that in coordinate geometry, once I'm looking at things like gradients of lines and so on, I've got the distance between 2 points and the gradient of lines. These are both things that a lot of students end up thinking about in quite a formulaic way. So when I'm tutoring, I often see students reaching for the formula and saying, oh, well, if I know, I can't annotate on there. If I know that the X and Y coordinates of my 2 points, I can just put them in this formula with a square root sign in it, and that'll tell me the distance between the points. And that's fine as long as they don't forget how the formula works. But thinking about it in this way and using this as the introduction to where the formula comes from, thinking of the 4 right-angled triangles that are wrapping around this square, and then saying, well, I know that if the change in Y and the change in X is the same for these two things, then I know that the two lines are the same length. It's just a really short step from there to actually working out that the length between them is going to be given by Pythagoras. And if you're familiar with the Enrich problem tilted squares, which I think we have shared in a previous one of these PTI sessions, the teacher's notes for that lay out in a really nice way how you can use this image of a tilted square as the basis for understanding Pythagoras's theorem and for students to be developing their own proof of Pythagoras. But it's not only Pythagoras that we're getting from this, we're also getting the perpendicular gradients thing, because I've got the gradient of this line and the gradient of this line. I know they're at right angles because this has gone along 6 and up 2, this has gone back 2 and up 6, and so the gradient of this line here is a third, and then the gradient of this line is going to be -3. And so by drawing different examples of tilted squares and using their coordinates to describe them, I can get from there to perpendicular gradients have to be the negative reciprocal of each other, because either the Y coordinate or the X coordinate is going from positive to negative, and so that's where your negative comes from, and that you've got Y over X instead of X over Y, that's where your reciprocal is coming from. So it's giving a really, really strong visual way of thinking about what's going on. We've got just a couple of minutes left. Charlie, I'm going to let you chip in with anything that you want to say and also give my voice a rest. And also, it'd be really lovely if you could describe to us, first of all, where we can find these problems on the Enrich site, where we can get more guidance about how to use them, and where we can find other related problems. Is that okay?
Sure. So I suppose one thing we'd like to emphasize is, what Alison said. Unfortunately, we have to go quite fast through these sessions just so that we can introduce you to a variety of problems. But we'd hope that students working on these problems would have a lot of square dotty paper with them, and it would be quite playful and experimenting, testing ideas, discovering things. And we've sort of rushed through that bit. I mean, you saw a bit of my square dotty paper, but we couldn't guarantee that you're all going to have square dotty paper with you, and because of the limited time we had, we've gone quite fast. But we think it's really important. The same way we want children to play around with numbers, it's really important to play with these shapes and notice and conjecture. So let me share my screen, and I'm going to share desktop. And so, can you see that, Alison? Okay, so on the Enrich website, everything is free, and you can go to the teachers page, and I'm going to click on the secondary teachers page. And we've been concerned about to talk about coordinates and vectors. So I'm going to go to problems that are linked to the curriculum. And actually, some of the problems that we've talked about are in the geometry and measure. So if I click on geometry and measure and go to angles and polygons, you can find that we've got problems here like square coordinates that Alison has just been talking about. And we've got, oh, wait a minute. And we have opposite vertices. So those are two problems that appear in the angles section. We can also find in geometry and measures a section on vectors, and here's where you can find vector journeys. But in the secondary curriculum, there's also a section on algebra, and if you go to functions and graphs, you can find problems like root to infinity, which Alison showed you as well. I'm going to be sending an email to the PTI this evening with a link to, I've got it written down somewhere, a page which has got links to, which will have links to all the problems. Can I lay my hands on it? I've started it. I'm going to add a couple of links to it. Here we are, 15382. So I'm going to be sending the 82. Okay, so I'm going to send you the link to this page, which no doubt the PTI will forward to you tomorrow or the next day, and it will have the links to all the problems, and it will also have links to the curriculum mapping document and a couple of other things that show what resources that Alison and I produced. So don't worry if you haven't made a note of all the problems. This is on its way. I think that's all I want to say, Alison. Is there anything?
That's fantastic. Thank you so much for sharing how to find those things, Charlie. And I think the key to finishing on time, it turns out that it's for me to be full of a cold and want to finish early. And by wanting to finish early, it then means that we miraculously finish on time. But I think that's all from us. I will just hand over back to Kirsty in case she's got any final things from the PTI. But thank you, everyone, for joining in. Thank you for all of the contributions to the chat. I've really, really enjoyed it. Thank you.